What you need to do is find out the net torque on the wheel, which is given in the figure. The net torque on the wheel is minus 3.55 Newton meter. Here, the negative sign indicates that the net torque is into the plane and therefore will cause rotation in clockwise direction. Curious to know how the answer is derived? Here's the explanation. Torque is the measure of a force applied on an object at a specific distance, which causes that object to rotate around its own axis. Let's look at the wheel and see what all we already have. We have the top view of a wheel, so we see two circles, an outer circle and an inner circle. Both the circles have the same center point, O. Let's say an imaginary axle is passing through this center O. Then we have the radius of the outer circle as B and the radius of the inner circle as A. Most importantly, we see three forces acting on the wheel at different positions. Two forces are at the circumference of the outer circle, and one force is at the circumference of the inner circle. These three forces have directions, but no names. If it is anything related to torque, the directions are extremely important, because torque is a vector quantity. Let's start by giving some good names to the three forces. F1. This is the first force and acts as the top of the wheel directing towards right. This force is tangent to the wheel or to the circumference of the outer circle. F2. This second force acts on the right-hand side of the wheel in the downward direction. This force is also tangent to wheel or to the circumference of the outer circle. F3. This third force acts as a tangent on the left-hand side of the inner circle. F3 makes an angle of 30 degrees with the horizontal in a counterclockwise direction. Now, let's determine the radius vectors for the forces. For this, let's consider x, y, and z as the points where forces F1, F2, and F3 act respectively. The distance from the center O to the point x is the radius vector of force F1. Let's call this R1. The distance from the center O to the point y is the radius vector of force F2. Let's call this R2. The distance from the center O to the point Z is the radius vector of force F3. Let's call this R3. Here are the values of all the quantities. F1 is 10 Newton. F2 is 9 Newton. F3 is 12 Newton. A equals 10 centimeters, which is equal to 0.10 meters. B equals 25 centimeters, which is equal to 0.25 meters. The values of the radii are given in centimeters. You need to convert these values into SI units, which here are meters. Torque is the cross product of radius vector and force. Here, vector r is the radius vector, and vector f is the force vector. The cross product indicates that the resultant vector is perpendicular to both vector r and vector f. The magnitude of the cross product is written as mod of vector tau is equal to r into f into sine theta. Theta is the angle between the radius vector and force. As seen in the figure, the forces are tangent to the wheel. Therefore, the angle between the radius vector and forces is always 90 degrees. Net torque is the summation of all the torques acting on one object. The direction of torque is determined by using the right-hand rule. It states that if you curl the fingers of right hand so that they follow a rotation from radius vector to force vector, then the stretched thumb points in the direction of vector product. Step 1. The angle between vector r1 and vector f1 is 90 degrees. The magnitude of vector r1 is b. Therefore, tau 1 is equal to b into f1 into sine 90. Now, sine 90 is 1. As per the right-hand rule, the direction of the torque is into the plane. Therefore, torque 1 is negative. Therefore, tau 1 is minus b into F1. Step 2. The angle between vector r2 and vector f2 is 90 degrees. The magnitude of vector r2 is also b. Therefore, tau 2 is equal to b into f2 into sine 90. Sine 90 is 1. As per the right-hand rule, the direction of this torque is into the plane. Therefore, torque 2 is also negative. Therefore, tau 2 is equal to minus b into f2. Step 3. The angle between vector r3 and vector f3 is 90 degrees. The magnitude of vector r3 is a. Therefore, tau 3 is equal to a into f3 into sine 90. Sine 90 is 1. The direction of this torque is out of the plane, and therefore its torque 3 is positive. Therefore, tau 3 is equal to a into f3. Step 4. Net torque can be found by adding the individual torques assigned with appropriate signs. So, tau net is equal to minus into the brackets b into f1, minus into the brackets b into f2, plus into the brackets a into f3. Now, if you substitute the equation with the values that we have, you get tau net is equal to minus into the brackets 0.25 meters into 10 Newton, minus into the brackets 0.25 meters into 9 Newton, plus into the brackets 0.10 meters into 12 Newton. So, finally, tau net is minus 3.55 Newton meter. Conclusion. We have the net torque, which is the summation of all the three torques, as minus 3.55 Newton meter. Here, the negative sign indicates that the net torque is into the plane and therefore will cause rotation in clockwise direction.